Hello, welcome back. In this segment, I will show to you an example that decisional Devi-Hellman problem is easy. So I'm going to take the group G to be Z star P and show to you that hardness of CDH and DL problems do not imply hardness of the decisional Devi-Hellman problem. All right, let me show you the algorithm that will help us to distinguish whether the input is a random number or a G power XY, right? That's basically the distinguisher that we are going to develop. How do we do that? All we are doing here is that we take G power X and to check whether G power X is a quadratic residue. We don't know yet, but it's easy to check whether something is a quadratic residue or not in mod P. Similarly, we do that for G power Z and G power Y and G power Z, okay? So let's assume G power Z is, for a moment, G power XY. Okay, in that case, what will happen? In that case, if these two are quadratic residues or any one of these two is a quadratic residue, then we know for sure this one will also be a quadratic residue. Okay, if both of them, G power X and G power Y, are not quadratic residue, then we know for sure G power Z, when G power Z is G power XY, it cannot be a quadratic residue. That we know. That means we can formalize it as follows: that if X is an even number or Y is an even number, okay, and we are going to return whether Z is also an even number or not. Okay, that's basically what I am checking here. If this is true, then I say you are feeding me G power XY. This is my distinguisher, okay? And I'm going to show to you this distinguisher is enough for me to show to you that in the group Z star P, it is easy to do the decisional Diffie-Hellman problem. Meaning decisional Diffie-Hellman problem is easy, even though discrete logarithm and computational Diffie-Hellman are hard. Okay, that's good enough. So now I will show you how I am going to do this demo. I'm going to run this demo T samples. Okay, T is an input. And I'm going to fix a small group just for demonstration purpose. Usually you should be working with a large group, but for this demo, it's enough to work with a small group. And all I'm doing is essentially generating randomly numbers X, Y, computing G power X, G power Y, G power XY. And also I'm picking a random Z, right? And I'm calling the DDH algorithm, feeding in with G power X, G power Y, random Z in one case, and in another case feeding it with G power XY. Okay. Then I'm measuring whether it was able to distinguish whether I'm feeding a random Z or a G power XY. That's basically what I am measuring. Let's do an analysis and show to you that whether the distinguisher is able to distinguish whether the input parameter, the last parameter here, is a random number or it's a G power XY. All right, let's do that. So I will call the demo DH for 100 samples. You see here, in all the 100 samples, whenever we passed G power XY as the third argument, it was able to tell the third argument is G power XY, meaning it's also quadratic residue. And it won't be able to tell, but it will tell you that G power XY appears to be G power XY, okay? But only in 50 cases, it was able to tell the input is a random. In the remaining 50 cases, it was not able to tell whether it was random or not. Okay, that means we have an interesting situation like this. Let's run it with another input, say 200 inputs. Okay, again, almost 50%. Okay, so now let me go back to the original diagram that I was talking about. This is from one of the previous segments, right? What did we achieve? We call the distinguisher, the algorithm A, passing in a random G power Z. We just randomly picked a number, basically. We didn't do G power Z, we just picked a Z. That's also enough, okay? And we compared against G power XY, of course, and we found out that the difference probability is half, okay, in our case, which means half is not a negligible number by no means. Therefore, we were able to show that DDH problem is actually easy. Let me summarize this more visually also. What did we do so far? I have 3 columns here. The first column is checking whether is G power X a quadratic residue. The second column is G power Y a quadratic residue. The third column, we are checking whether the third is G power Z a quadratic residue, okay? So I wrote 8 combinations here. And why did I mark only 4 of them? Let's assume the third column was, for a particular run, a random number, okay? Suppose the random number satisfies this property that g power x is not a quadratic residue, g power y is not a quadratic residue, but g power z is a quadratic residue. In that case, we know for sure that the third column is a random number, right? Because if they were feeding g power xy, we would not have got 1 as the quadratic residue status for g power xy. Okay, given that g power x and g power y are not quadratic residues. Okay, that means the 4 out of 8 scenarios where we can distinguish whether the third argument, meaning the g power z, is it truly a random number or is it a g power xy? Okay, that's the reason I said the probability difference is bounded by half. Okay, what did we achieve? We achieved the fact that DDH is easy, even though we believe both CDH and discrete logarithm are hard problems in this group. That's all. Thank you very much.